Okay, picking up where we left off. Tuning into 98.1, and if I'm on stereo, I go to mono, we get rid of the pilot tone on there. But you can see we still have a really bad waveform. Now, we're looking at the record outputs on the back of the receiver. So what we should see right now is a perfect 400 hertz sine wave, because that's the modulation we have on there right now. And for some reason, we're getting this weird looking waveform. So what could be wrong with the tuner, you wonder? So let's look around first. I don't think it's a switch, because if you look at the switches, if a switch is dirty, normally one channel would look different from the other. And you can see they're superimposed over one another. They're pretty much exactly the same. So whatever this distortion is, it's being caused equally to both channels. So I wonder what that could be. So what happens if we increase the amplitude of the signal? Well, it makes the signal bigger, but it doesn't straighten it out any. So let's look at the simple things first. Let's turn this thing around. Let's look at our front dial and let's see what's going on. Boy, this receiver's so large I can't even get it all in frame without taking the camera off of the mount. But we're interested over here. So first of all, we have a fairly good signal on there. One thing I noticed is that the dial accuracy is off by a little bit. We have a 98.1 megahertz station that we've created here with our Sencor SG80, and you can see we're not at 98.1. We're actually at 97.9, roughly 97.8. So the dial accuracy is off a little bit, which means our oscillator is off a little bit. But I don't necessarily think that's the problem. Now the other thing is our tuning dial is centered, our tuning centering, and you can see it's pretty well centered there. So let's take a look and see what we can do with some of our switches. And you know what? I see the problem right now. At least I think I see the problem. Let me get the faceplate. So, yes. Looking right about here, these two switches here line up with these two buttons, and you can see we have the muting off, and we have this button called multipath pressed in. So let's see what happens when we push that button and we turn it off. How about that? Perfect waveform. It's fixed. So exactly what is the multipath button on a tuner? Well, this is something that can be different depending on the receiver. Usually on some of the higher end receivers, you'll see this button. And this button can perform two functions based upon the design of the receiver. In most cases, when you push in the multipath button, all it does is it changes the signal meter. In other words, what it does is it converts the signal meter into from a signal strength meter into a multipath level indicator. And what you do is you would adjust the tuning until you get the minimum amount of multipath distortion. So what is multipath? What multipath is it's a characteristic of radio waves. When you transmit a radio signal from a tower, from an antenna, what happens is all of the buildings and all of the objects between that antenna and between your receiving antenna and your receiver, those things can affect that signal. Any of you who have just a portable radio with a telescoping antenna, you can attest to this by, if you move that antenna around, or even if you walk around the room near the antenna, you'll notice that the signal changes. It'll get stronger and weaker, and sometimes it'll get distorted and not distorted. And this is called multipath distortion. Now, it's the most prevalent when you're in like a city with big buildings and metal objects and so forth. And really what's happening is the direct signal from the antenna, or from the transmitting antenna, that is going directly to your receiver. But also a portion of that signal is being reflected off of those objects that we just talked about. And that reflected signal is somewhat delayed in arriving at your radio or your receiver from the direct signal. So what happens is you have two different copies of the same signal that are just slightly separated from one another in time. And therefore you'll get this distortion because you'll receive kind of a double image. And that causes what's called multipath distortion. Multipath should give it away. Multi meaning multiple, path meaning paths, right? So you have the path directly from your transmitting antenna, and then you have the path from the transmitting antenna reflecting off of an object and reflecting into your receiving antenna. And that causes that distortion. Now that button was a way that you could visualize that. So what it is there's an extra circuit. In some units it's discrete components. In other units like this one, it's part of an integrated circuit. It's a function built into one of the chips in there. And what it'll do is it will output the multipath signal. And it does some little math tricks to get the difference between the multipath and the direct signal and display it on your signal strength meter. But in this one, it's a little bit different. Not only does what it does is it allows you to listen to the actual multipath signal. And when you listen to that signal, it sounds distorted, and the whole idea is you're supposed to adjust the tuner until you minimize that distorted sound, and then you turn it back off. And in a perfect world, whether you have it turned on or off, you shouldn't hear a difference, but in the real world you do. So that's what we were seeing. So if I turn it on, you see what it does, right? If I turn it off, perfect signal. And that's the way it's supposed to work. So really, I had to troubleshoot myself, not the receiver. So that wasn't an issue. And we'll look a little bit about what that circuit does. My bigger concern right now is our dial accuracy. So we're going to go through the alignment process on this. And most of it we're just going to be verifying because this thing seems to be working okay. But at least for the dial accuracy, we'll adjust that and take care of whatever we need. So stay tuned. Okay, before we even get into this, I see a problem. Here's your tuning string. One of them, it's supposed to go around this pulley, but look, it's going around the screw, and that's not good. And here it is again going over the screw instead of the pulley. So at some point in this thing's life, the dial cord came off of the pulley, and this is why I'm glad we didn't go tuning around and so forth. So we're going to fix that. So let me put this back up on there, and I'll be right back. Maybe this will fix the dial accuracy problem too. Who knows? Okay, that's better. So just using I just loosened the screw here on these a little bit, and then just used this little hook and just got under it and kind of helped to guide it back up on there very carefully. And it looks like we're okay. However, when we're tuned on station, let's bring this down, we're still off. So we're going to have to adjust the oscillator. Now, normally this would just be a simple little adjustment of the oscillator, but we're going to go through the alignment process just to see how it works, okay? Because it's kind of interesting on these tuners. Okay, to quote what I believe was the Mad Hatter in Alice in Wonderland, we will start at the beginning, and when we come to the end, stop. So let's look. So the first thing they have you adjust is the AM. So let's switch over to AM. And they want us to look at the outputs of the record jacks as we normally do. Set the function switch to AM, and we're going to connect our signal generator through a 1K resistor to the AM antenna terminal. Alright, the first thing they want us to do is set the dial scale here on 60 for 600 kilohertz. And the signal generator, of course, we want a 600 kilohertz signal with a 400 hertz tone. And they're saying 100 dB, that's dBF, and that's basically what they're saying is they want a relatively strong signal. And then they want you to set the SX-1250 dial indication and AM frequency for 600 kilohertz. Adjust T3, which is down here, for maximum reading on the meter. And then they want you to set the dial indication to 1400 and adjust TC1. So that's what we're going to do. Now the very first thing that we're adjusting with that T3, if you look down here, that is your AM oscillator. So if we look here, we're at 600, and if we look here, we got a pretty terrible looking waveform. And if I put the whole thing on camera here, and those of you with mobile devices are going to have a hard time seeing, if I tune this, you can see right there is where we're centered on the signal. And even the signal meter, you could see, is peaked out right there. So the dial accuracy is off. But you have to follow what they're telling you. We want to go right on 60. We're on 600 kilohertz. We want to center it perfectly. And then watch what happens when we adjust our oscillator. All right. I hope I'm in frame here. So let's adjust this, and you can see we can bring it right in. See how I went through the peak? We're going to take it right back till we're right on peak there. You can also use your signal meter for when you're on peak, because you'll see when you pass through that, the signal meter, I don't know if I can get this in the shot or not. Here's your signal meter. I hope everything's in focus. It's probably not, but watch what this signal meter does as we pass through. See that? And right there's that null point. We pass through it. So between our waveform, and if you use a meter like a VTVM with a with a needle movement, it's really easy to find the peak on it. But the only thing is sometimes the static will throw that off a little bit. So you're better off looking at your waveform and at the signal meter at the same time. So that's good. Now we're on frequency. The next thing they want you to do is go up to 1400 kilohertz. So we're going to move this down to 1400 like so. We're going to put it spot on 1400. And we're going to change our signal generator up here to 1400. So the one thing I don't like about this SG80 is that there is no shortcut to, you have to rotate this knob a million times to get on frequency. And you can see how close that one is. That oscillator, at the top end, the oscillator is pretty close. And our dial accuracy is not bad. Might take just a teeny little tweak, but it's going to be pretty close. And what they want on that is they want TC1 for that. So that's going to be the high-end oscillator. And it's going to be kind of touchy. See that? The capacitors, the TCs, they're always touchier than the coils. And if you pass through it, you can see there, we're right on it now. Very hot. Okay, and you can see again our meter. Now they want us to go back down to 600 again. Now that our dial accuracy is set, we're going to go to our 600 and we're going to set our IFs. All right. See, AM is easy to do compared to FM. All right, and you can see we're right on. And what we're going to do now is we're just going to set this for T3 and T4. Once again, we're going to adjust them. So this is the RF coil. We're just going to set that for peak. You see, we just got a tiny little bit out of that, not much. And then they want you to adjust the bar antenna. And what that is, we move this around just a little bit. On the AM bar antenna, you can see it right here. Down in the front, there's a slotted slug in there that you can rotate. And usually it is extraordinarily tight. And if you don't watch, you can crack that core. And in addition, most plastic adjustment tools will not be strong enough to adjust it. So you kind of have to use a metal tool, which will throw off your settings. So what you have to do is you have to just adjust it slightly with a metal tool, like a screwdriver, and then come out and see where you are. And usually it's not going to need, see, this is too tight. I'm not going to even force it because it's going to crack that slug. It's pretty good how it is. But you'll find that a lot of the times the plastic in here will kind of shrink down with age, and that slug will just get wedged in there. And I normally don't like to force it unless it's really badly out, and it doesn't seem to be. So that's done. Now they want you to just go back through, and they want you to go back to 1400. So we're going back up to 1400. And I'm going to rotate, rotate, rotate. That's why I don't usually use this thing a whole lot for AM when you're dialing back and forth. Use one of my other signal generators. And we'll go back to 1400. Tune it in, and then we'll do TC1, TC2, and TC3, which is those three across the top. We'll bring it right in, and that's it. So we'll come here, and we'll adjust these three right here. And you want to leave the metal shield on this thing when you calibrate it, because when you align this, if you align it with the cover off, it will affect things a little bit. There we go. So this one's already peaked. And we'll look at this one here. And if it's peaked, I'm not going to touch the other one because we already adjusted it. I can't get on this here. There we go. This one's kind of noisy here. That's the other way. So right about there. That's about all we're going to get out of it. So it was pretty much on. And I didn't expect these to be very far out. So the dial accuracy at the low end was the only part that was out. And it was just out by a tiny amount. So your AM tuner is done. So now it's time to go to the FM. Now before we start this, I got to give you a little word of warning. And that is, when you look at this or any instruction manual for the alignment procedure on an FM stereo receiver, you will see a configuration that they want you to do in order to perform the alignment according to the instructions. What you're going to find out is that you may not have the same test equipment that they did when they did the alignment in the factory. That doesn't mean that you cannot do it. What it means is you may have to modify your alignment procedure based upon the test equipment you have. And so, for instance, sometimes when you're trying to, for instance, look at a S curve or something like that, you may not be able to do that. For instance, using this SG80, it might be a different procedure because, for instance, on this one, you could never do an S curve on it because all of that takes place inside of an integrated circuit chip. You really can't get into that part. It's in the chip. So the test points that you use require a different type of signal. And that's why you have to sometimes modify your test equipment or modify the use of your test equipment or the procedure you use to the circuit that you're aligning. Now in this case, we should be able to pretty closely mimic what they have here, and we'll try to do that. But just keep that in mind. You're not out. You're not out of luck if you can't. If you don't have the exact same test equipment, you can modify. Okay, they want us to switch to FM, and they want us to connect through the 300 ohm dummy load to the 300 ohm FM antenna terminals. Now, when they talk about a 300 ohm dummy load, sometimes in some service manuals, they will actually show you a little network they want you to build, okay, of capacitors and resistors or whatever to make that dummy load. So you can see all the different ones I have. For a few, I have several bins of these from different setups. But for this one, you can actually just use one of those little balance, little connect, to go from 75 ohms to 300. Now, understand, my SG80 has a 75 ohm termination on the output, or is designed for a 75 ohm load. Most commercial grade, test equipment like this, they're designed to go into a 50 ohm load. In most cases, it doesn't make a big difference. But understand, if you're adjusting something that has a level meter or something where you're very precisely trying to measure some sort of a signal level, you're going to have to convert that somehow. And I go into this in other videos. But if you have something like the SG80, or if you have like a Sound Technology 1000A or an SG165, those all are designed for, FM stereo, and they have a 75 ohm output. And then all you use is one of these little balance. And you can find these even at like the hardware store. They're for connecting a 75 ohm coax cable to a 300 ohm connection. And a lot of televisions in the old days used these for VHF, and you can use that. So long story short, just go ahead and get one of those. This is what we're going to use. Now, again, they want to look the AC voltmeter to the tape 1 record jacks, and they want the FM signal generator for 100 dB output at 400 hertz and 100% modulation. So they want a pretty strong signal for starting. Okay. And we're going to start out at 87.4 megahertz. Okay, I am now at 87.4 megahertz, both on the tuning dial and on my signal generator. And you can see things are not right. We have a very weak signal being displayed here, and our centering indicator is off. So this is showing the problem that we had here. So if we go through here, we're going to adjust the T5 core. Okay, and these are going to be up here on the back of the front end module. So we're going to go in here, and you can see where T5 is right here. And these are the bottom view of the FM front end. So we're going to have to rotate this receiver around to be able to get to all this. Okay, hopefully we can see what's going on here. And if we line up our page here, we can actually see where we're adjusting. Okay. And actually, this is the orientation they want. So you can see they want it, it's going to look like this. Here's your tuning gang right here, the gears, and you can see it up there. So this is where we're going to adjust. Now, what we want to do is we want to set, we're at 87.4, and when we want to adjust T5, which is going to be, looking here, there is T5. So it's going to be kind of over there. You can see it. And it is an actual slug, so we're going to need an alignment tool for that. I'm going to guess it's going to be this green one. Let's see if I'm right. Yep. And what we're going to do is we're going to adjust it for maximum indication on the signal meter. So let's go over here. Let's look at our signal meter. And let's see if we can get maximum indication. That is not maximum indication. And look how far off we were. Yeah. And you can see even when we peak it out, the centering comes in as well. Okay. So there you go. And that's pretty close. Okay, so we got that, and if we look on our scope, what's going on at the same time, we have a pretty nice looking waveform there, and it's much higher amplitude than when we started. Okay, so that's done. We then want us to go to the T5 core. Okay, let's see what it says. I'm sorry. They want us to go to 8 dB output, so they want us to seriously lower the signal down. And you can see we're not properly centered. Okay, so we're going to have to bring that in a little better. There, I was just tiny hair. Okay, and they want us to adjust T1, T2, T3, and T4 for maximum reading. And you can see T1, T2, T3, and T4. So we're going to go counterclockwise, these adjustments. Okay, so let's see. I don't know if I can get everything in shot. We'll try here. And it's going to be really hard to see the meter, the signal meter, while we do this, but I will be also looking at this signal meter while we do this. And we want T1, which is kind of hard to get to. And this one's a little bit stubborn. And what you'll find is sometimes these slugs will get stuck in here. And we just don't. There we go. See if I can go up a little bit more. I just want to start to get a little bit of a signal on there. Okay. And there's the peak. And you can just kind of see how it gets just a little bit taller. It's very hard to see, but it's there. Okay. T1. T2. That's the wrong way. So again, that one was peaked already. T3. Look at that. That was out by quite a bit, wasn't it? Okay. So that was out. That one was way out. And T4, that one doesn't seem to be too bad. That's going down. That's going down. And right there's about the center of it. Okay. So yeah, a couple of these were out. They needed to be adjusted. So now we're going to go to 106 megahertz and we're going to crank our output way up again. Okay, everything is at 106 megahertz and you can see how it's kind of folding over. We are not right on frequency. So now we have to adjust TC, which is the capacitor, TC5, which is going to be this one right here. You can kind of see it in there. And we're going to adjust that for center frequency and maximum amplitude. And this is, again, the capacitors are always touchier. There you go. See how easy it is to pop right through it? And there it is. So you're right on. Okay. So now we're on frequency, and now they want you to drop this way down. Way down. And you can see we're still not on, we're not dead on now, so now we can adjust it even better. So they have you start out with a really strong signal in case you're way off, way off frequency. And then they have you lower it way down. And you can see, and I'm going to lower it even more. And see, I'm still not perfectly centered. And what you want to get is you want to get static on both sides. Okay? So you'll see what's going to happen here as I adjust this. As I zoom in on this closer and closer, I will have the same amount of static, of static on the top and the bottom. Now I'm dead on frequency. It's perfect. Okay? That's what they're looking for. Now once we get that perfectly centered, we're going to do TC1, TC2, TC3, and TC4. So it's going to be the same process, but we're adjusting the capacitors now instead of the coils for the high band. So you can see TC1, TC2, TC3, and TC4. So TC1. And again, these capacitors are so touchy. I hate to even adjust them, but you kind of have to. And you can see we just it's pretty much on. If I move it too much in either direction, it starts to drop. So that one's on. TC2. That one, again, was right on. TC3. And these are so tiny, these little slots on here. Okay. Nope. That one was right on. And then TC4 is right here. Yep, it's right on as well. So those were all good. And then we're going to leave that all there, and everything's perfect. So that's good. Now they have you just kind of go through it one more time to eliminate variations in the meter reading. So they basically want you to go one more time and fine tune it. Now once we've done that, they want us to go in and adjust T6, which is this one right here, and just for maximum signal. So we're going to find T6, and it's kind of buried underneath a cable here, which I don't like moving cables and things around in these very much, so I try not to. And we're just going to go for maximum amplitude once again, and I think we're right there. As soon as I pass through that, you can see the static kind of changes. I'm going to leave it right like that. Okay, so that one was right on. So yeah, a couple of them were off by a little bit, and it affected the dial accuracy, but we're good now. Okay, now the next thing they're going to have us do is we're going to adjust the detector. And in order to do this, we're going to have to connect a voltmeter to test point 43. And in order to do that, we are going to have to take the cover off on this. So we're going to do that. And again, once we're past the RF stuff, what you're going to find is that you don't have to worry so much about noise getting in there, because everything that gets into the IF section, by the time it's up in the IF, you have pretty high signal strength. So you don't really have to worry about the capacitive coupling and things of the cover as much as you do when you're dealing with the RF, in the lower signal levels. Before I get this cover off, I want to kind of show you all something. If you look right here, this says FM discriminator transformer. And in a previous video, I referred to the detector as the discriminator, and I got chastised for that because it was not a discriminator. It is a ratio detector, if you want to get technical. And this even has a quadrature detector in it. But anyway, the word discriminator is an old word. It comes from the old style, some of the earlier circuits that were used to detect the audio on the FM carrier. And that name has stuck. So you can see, even though this is not a true discriminator circuit like you would see in an old tube radio, they still call it that. And when you hear that term, that doesn't necessarily mean that it's a discriminator circuit. It just means they're talking about FM detection. So just keep that in mind when you hear that. And if you hear me use that term, that's why I use it. Okay, it's force of habit. But yes, this is not a discriminator as per se. Okay, the old Foster-Seeley discriminators were a little bit different, and there's different versions of discriminators, ratio detectors, quadrature detectors, and so forth on these analog tuners, and they're all a variation of a very similar circuit, and each one is kind of an improvement over the other. So just so you know that. Okay, the next thing we want to do is we want to turn VR1 and VR3 all the way counterclockwise. So that would be VR1 and VR3, and they're both rotated counterclockwise. You then want to tune the tuner to an area of the dial where there's no signal. So what I've done is I've just shut off the signal generator altogether, and there's no signal coming in. And I moved it to a part of the dial where there's the least amount of interference or any kind of anything. And then what we have to do is we're going to adjust this discriminator coil, or this detector coil right here. We're going to adjust that until our tuning indicator meter is dead center. Now, the camera is a little bit above the meter, so you're not going to see what I see when I look straight on. But what I'm going to do is I'm going to adjust this, because it is off, until it's straight on. And there we go. Okay, because if you remember, it was showing that it was a little bit off earlier in the video. All right, the next thing we're going to do is we have to set up our signal generator once again, and they want 98 megahertz at 60 dB output, or 60 dBF. And what that's going to do is we're going to do our adjustment at the center of the tuning scale on the dial. Because between 88 and 108 is 98. So they just want you at the center part of the dial, the sweet spot. We're going to turn this on. And they don't want any modulation now. They just want an FM carrier. So all we're going to do is we're going to set 98 megahertz. There's 98. They want 60 dB. So there we go. And we want to make sure we're right on. And you're not going to see any output on the scope because there's no modulation. It's just an FM carrier. That's it. And what we're going to do right now is they want you to take T2 upper core, and they want us to measure, they want us to connect the meter to pin 43, which is right here. And pin 43 is the output of your FM detector. And they want you to measure between there and ground. And what we're going to use is what's called a FET-VM. It stands for Field Effect Transistor Voltmeter. This is basically a solid state equivalent of a VT-VM, or vacuum tube voltmeter. And Don't confuse this with a VOM, which is a standard volt ohm meter, like this triplet that you see all the time. If you notice on this, it has the 20,000 ohms per volt DC and 5,000 ohms per volt AC and so forth for the scales. This is not like that. This has a high impedance input, just like a VTVM, and it will do all of the functions of a VTVM. And one of those functions is called a null meter. So if you look, if I ground out the probes, you can actually set the meter that 0 volts is the center of the scale like that, which is beautiful because you can check positive and negative voltages. And that's what they're going to have us do. So now we're going to connect this, and you can see it's off. And what they want us to do is to adjust T2 upper core, which is this transformer up here. And there's two sides to this alignment tool. This one kind of has a little ridge on it, see? So it will only let the tool go down into the slug that far. The second one is shanked down a little bit, and what that allows is there's two slugs in this coil. So you can go through here, push through it, and now there's a lower core, and we're going to adjust that next, but this one we got to do first. And what they want us to do is adjust until we have 0 volts. So we're going to do that right now. Okay. Very touchy. And there it is. Now when you get it really centered, then I can go to the most sensitive setting on there, and I can even get it closer. And this is something that you can of course use a regular DMM, you know, your digital, your fluke meter or whatever, your digital meter. They have high impedance inputs too. And again, you just adjust it till it says 0 volts. But I just like watching the needle on these. All right, and you can see how sensitive it is now because this is tiny little voltages. The full scale of this meter right now is only plus and minus 150 millivolts. So this is like, you're adjusting it to within microvolts now. That's pretty close. I think that's as close as I can get it. Okay, the next thing we're going to do here is we're going to connect a T-piece in here from our signal from one of the channels, and we're going to connect it over to a distortion meter. Now, if you don't have a distortion meter, obviously you cannot do this test. And of course, this is a very expensive one, but there are other ones out there that you can purchase online, you know, used ones. Leader makes them. Even Heathkit made a harmonic distortion meter. Sound Technology, there's a whole bunch. But anyway, we're going to adjust that, and we're going to adjust T2, the lower core, for minimum distortion. So right now you can see we have about 0.18, almost 0.2% THD. And what we're going to do is we're going to go to that lower core of T2, and we're just going to adjust this until that gets as low as possible. And you can see there, that's very good. I don't know if, yes, you know, I'm going back through it. It's very hard to get because the alignment tool is plastic and it flexes. So it's really hard to turn it. And once it lets go, it kind of flings through there, kind of spring action. And you get, because these slugs are kind of tight. So we're just going to adjust that down as far as possible. That's about it right there. That's all we can do. Perfect. And see, you really can't see distortion of that magnitude, you know, on there. Now what you could do is, if you have a modern digital scope, you could go into the FFT function and you could adjust for the least amount of harmonics. As long as the problem with that is a lot of the oscilloscopes with the FFT mode, they can't get down far enough with signal level to really measure that. Some of them can, but I've found that it kind of gets a little bit dicey when you have real small signal levels like that. But again, you can technically do that. And if you have a higher quality digital scope, absolutely you could do it. Okay, so there's different methods, but that's the easiest if you have a distortion meter. Okay, now is where it is helpful to have a calibrated amplitude on your signal generator. And this is where mismatches between your cables and so forth, and loading, if you have a 50 ohm signal generator going into 75 or 300 ohm input, you'll see a little bit of a difference. It's not huge, but you will see a little bit. And in that, if you want it to be absolutely perfect, you can create one of those little L-pad matching boxes like I did on a video on a while back, and to get it perfect. But anyway, this one has 75 ohms, so it's pretty accurate. And what we're going to do is we're going to go to 100 dB signal, which is what we have, 100 dBF. And we're going to adjust that VR1 that we originally had turned all the way counterclockwise. We're going to adjust it clockwise now until we see a signal meter strength of 4.7. All right, so VR1 is that one right up here underneath this T1. And you can see it's not reading correctly right now. It's reading low because we have the pot turned all the way down. So we're going to adjust this until we see 4.7. So, and if we go up like this, and 4.7 is going to be just a little bit over 4.5, isn't it? So there you go. And that's going to indicate a full signal. Okay? Okay, when we're talking about the stereo alignment for this receiver, this is kind of an example of what I'm talking about with you have to have the correct test equipment, or you have to modify the procedure based on the equipment that you have. So using the SG-80, it does not have a pilot output on it. So what they're talking about with the pilot, your 19 kilohertz pilot signal is kind of where all your phase relationship and everything is coming from in your stereo composite signal. And what they're asking you to do in this procedure, you can see, is you're going to create a Lissajous pattern. I hope I'm saying that right. On your scope using XY mode. And what they want is they want the X mode, or the horizontal axis, to connect to the 19 kilohertz pilot tone. Well, we'll look at it here. You see what they're doing. So you're coming out of your 19 kilohertz and you're going into the horizontal of the scope in XY mode. And then you're coming out of the vertical, so you have channel 1 and 2 in XY mode. And those of you who don't know about XY mode, you may want to look that up first. And then you connect the vertical, or the Y-axis, onto or terminal number 9. And you can see that's what I've done here. Now we cannot do that with the Sencor SG-80 because it does not have an output for the 19 kilohertz pilot tone that it generates for the composite signal. Now there's other ways to get around it, but if you want to just blindly follow the directions on this, you can't do it if you don't have the correct signal generator. So what I'm going to do to make things, at least to let you see the correct way to do this according to the instructions, is we're going to use the 1000A. And it in fact does have a 19 kilohertz output. Okay, so we're coming out of that, we're going to the x-axis of the scope, and I think you could just see it over there. And you're coming out of the RF, and we're generating a stereo signal on 98 megahertz at 60 dB. Okay, and that we're just feeding right into the antenna jack, and we're tuning in to 98. And we're tuning very precisely onto center, and we should have a stereo indicator light. And if you do this all correctly, And this is not a very good example because I can never get this combination to look just like the instructions. But what you'll get is what I call the butterfly pattern. So you can see there, I call that a butterfly pattern because it kind of looks like butterfly wings. But anyway, mine is kind of squished in on the sides, and it always does that, and it's probably me. But when I use this scope with that, the 1000A, I'm either not setting something correctly, or that's just the way it is on this one, just because of the way that scope is. But anyway, it's still going to work for what we're looking for. What you're looking for is you want a nice crisscross pattern on here, and you can see your channels, and you can see where it kind of crisscrosses and folds over. And you look, we have that same thing down here. I just can't get it to expand properly with my scope. And when it's not right, I'll show you what it looks like. What you're going to do is you're going to adjust that VR2 potentiometer, because if you remember at the beginning, we turned it all the way counterclockwise. You want to adjust it until it looks like that. So you want these nice sharp looking lines that crisscross, and your butterfly wings on either side, which mine are squished. My butterfly got stepped on. But it works. And if it's wrong, what will happen is when you start getting just barely out of adjustment like that, you'll see these lines will flutter, and you'll see that they'll get kind of blurry. I don't know if I can get in there close enough to show it. And if we adjust R2 even further, you see how they close together, and then eventually it just oscillates. See that? And if I go the other way, it flutters, and then I get through the part where it's nice and straight. You see those are nice sharp looking lines crossing. And if I go other way too far, same thing's going to happen. You see here, it goes into oscillation again. See that? And you lose your stereo beacon. So when it's like that, if you notice, there is no stereo signal. When we bring it in, going the wrong way. Here we go. And you have to just sneak up on it. See how they're spreading apart? And there it is. And now that we have that, we have a nice stereo signal. Okay. And that's pretty much what you're looking for. Now, again, this is not an ideal looking waveform. And I'm just not sure why, but it's just the way it is with this test equipment. Again, you have to learn your test equipment. Now let's look at how I do it without using XY mode on the scope. Okay, so if you just have a basic stereo multiplex generator, and again, you have to have a stereo multiplex generator to do this. If you don't have at least that, you really shouldn't attempt to do the multiplex circuit of this unit. And this works pretty well. It's not as accurate as the butterfly pattern, but it works. So what you do is connect up your normal stereo composite signal, which is right here, and get it onto the scope. And we're now back to the record out jacks on the back of the receiver. And you can see I have the two channels superimposed on one another. You want them to be perfectly over top of one another like that. And what we're going to do is we're going to go over to the signal generator, and most stereo signal generators, if not all of them, can do this. So what we want to do is we want to switch over to left minus right. When we do that, you're going to see that the left and right channels will go 180 degrees out of phase from one another. At that point in time, what we're going to do is we're going to just adjust that R2, which is down here, right here. We're going to adjust it until it looks like what you're seeing right now. I'll show you what it looks like when we're out. Okay. if we're not over top of it, if the phasing isn't right, that's what's going to happen. You lose your signal altogether. If you get right on top of it, see, I'm passing through it, and right there we're centered over it, and we have a perfect signal. It's as simple as that. Now, again, this isn't as perfect as the butterfly pattern, but it works, and I doubt that anybody will know the difference. It should work just fine. So that's it. Now what we're going to do is we're going to adjust VR3, which is this one down here, and this is our stereo separation. So we're going to go to right channel only, and you can see, because that pot is maxed out all the way counterclockwise, we still have a little bit of bleed over signal there. See this one? It should be a flat line. So if I go like this and I rotate that pot, you can see right there, you can flatten it right out. If I go too far, it'll go the other way. See that? So we want that to be perfectly flat, just like that. Okay. And then if I go to left channel only, of course my trigger is not working. There we go. And it's the same. And it's as simple as that. And if we go to left minus right, again, 180 degrees out of phase, everything's set. So it's as simple as that. Again, it's just a matter of what test equipment you have and how you can adapt to it. Now, this really has some cool things you can do with it if you can get into the IF stage and so forth. But the problem with these modern receivers, not really, with the ones that have all integrated circuits, a lot of the things that you need to tap into, like for instance to generate an S-curve or things like that, they're inside the chip. So you really can't see those signals. They're self-contained. It's a different circuit design from, you know, the all discrete ones of the past, you know, prior to this. So hopefully that gives you a little understanding of that. Now what I will do is I'll swap out these couple little orange caps. As a force of habit, I do it, and we discussed that many times. And this thing's done. It's ready to go. Okay, we are all back together, and I can barely get this thing all in the frame here, because the arm on my camera mount only extends so far out. But you can see right now, I have a 15 microvolt signal going in here, and you can hear it with static. Okay, you hear that? And let's go down and we can look at the waveform here as I rotate this. So let's go down. There's 1.5 and there is 1 microvolt. And although there's a ton of static, you can still hear the tone. When we get up around 2.5 microvolts, you can actually hear it pretty strong. Okay, now let's put some static on there so you can see it and you can hear it. However, let's do something. And you can see when I push the multipath button, the sound goes away. I take it out, and this is what should happen. So even though it is a weak signal, that has nothing to do with multipath. Multipath has to do with the same signal that it's being transmitted twice or multiple times at different timings, so the phase is going to be off. And if there were multipath in here, you would actually hear that multipath signal. And it would sound like distorted audio. And the idea is you're supposed to put this in and rotate your antenna until you minimize the amount of multipath. Okay. Now in some stereos, you know, the really high-end ones that have scopes on them, you can actually see this on there. Kind of what we're looking at now. And so let's hook this up to actual FM and see. Of course, I don't have an adjustable antenna. My antenna is a vertical antenna. It's outside, and since it's non-directional, you can't rotate it or anything. But I can show you an example of what multipath sounds like. Okay, here's a really weak station that we're tuned into. And you can see it's hard to... There we go. And you can see there's no multipath in this station because you can see how it disappears.
Tell me what to do in Charleston for the weekend. And it's like, it's just never been available before.
Okay, let's see if we can find one with bad multipath. I have to get talking or something, because if I get a song, unfortunately.
Wait, you're a yoga instructor now? Yes, and I love it.
Okay, here's an example.
It feels so good to be helping people improve their lives, and I basically get...
Hear that little bit of audio in the background?
And you do everything at your own pace. Once you're certified, you do what you want.
So what that is the multipath that you're hearing. You're hearing the phase difference between the multipath signal, or the reflected signal, I should say, and the direct signal. And if we had an adjustable antenna, what we would do is we would push that button in and we would rotate the antenna until we minimized the amount of background noise. So that's what this is supposed to do. It's kind of a gimmick because, hey, I can rotate the antenna and listen for the station to sound clear, right? In addition, some of the lower end units, instead of hearing the multipath, it just changes the function of the signal meter, and the higher the meter deflects, the more the multipath there is, and you would rotate your antenna until you minimize that. So that's what that is. Okay, let's fire up our Stranger Danger song, and then we'll do a couple tests on the amplifier before we wrap this up. We got it. All right, let's do some amplifier tests and we'll wrap this video up. Okay, we have all the noisy test equipment with all the fans. We have our 1 kilohertz tone going in, and let's see how much power this thing can do. And of course that purple line that's coming up, the purple and the tan line, that's your wattage, but this thing's so powerful it actually goes off the scale, and I would have to rescale that math formula. But we can look at the RMS value here, and you can see right around 38, 39 volts right there. We'll call it 38.5. Okay, so 38.5 squared divided by 8. 5 squared divided by 8. 185.28 watts. And at 1 kilohertz, I would expect that. Full bandwidth, it's going to be right in there with that 160, 165, what it's rated at. Let's take this up just before clipping and let's see what our THD does. Okay. So here is 10 watts per channel. Right there. There is 50 watts per channel. It's about 68 watts per channel. And like I said, this is a detented control, so I can't really control it a whole lot. And here's just before clipping. And there's your maximum. I don't want to leave it up there too long. So the distortion figures on this are excellent. Everything looks good to me. And of course I can do the million audio tests that I've done in other videos, but we all know how this thing's going to perform. It's, you know, it's perfect. So, sad to see it go because it's not mine, but I'm happy that it's going to go back to its owner. He's a friend of mine, and I know he's going to enjoy having this once again. And hopefully he'll bring it back up into his house and enjoy it for another 30 or 40 years. So anyway, until next time, I wish you all peace, joy, happiness, and good health in your lives. And man, I don't know what all I'm going to do next. I have so many things to choose from now. I'll have to figure it out. Anyway, stay well, everybody. Bye-bye.